Okay, so we're going to roll with this logistic loss now. Now that we've let that sunk in, what we're going to do is, okay, this is the logistic loss on a particular example, but what we actually want is a loss function over all examples. So maybe I'll write this as, the loss function over all x. So I'll use capital X to refer to all the x examples, and capital Y to refer to all the y, all the outputs that are paired to them. And so what I would say here is, okay, the total loss over all examples here would be the sum over each individual example. So maybe let's say that there's n examples, and I'll zero index them. So from k equals 0 to n minus 1 of the logistic loss. So I guess I'll just copy this equation here. So the logistic loss on a particular u and so actually what I'm going to do is sum up the losses over every single example, and that's my overall loss function here. Oops, forgot one, so this should be a y-key here. Okay, so I'm going to sum up the losses over every single example that I have access to, and I'm going to try to minimize that whole thing, the whole sum. So if it does badly on one example, that's okay if it does pretty well in the others. So we're going to aggregate all of the losses and try to minimize this expression over the sum of all of them. So let me show you first visually how the minimization works, and then I'll explain it a little bit in math. Okay, so one thing we have to be aware of is we have something called a learning rate. So let's refer to. So we have a learning rate, alpha, which is how quickly we move across our parameter space. So I'll call it that for now. So we're going to jump from one location in our parameter space to the next, and alpha controls how quickly we jump. So let me show an example here. And actually, let's wait for this to reset in a moment. So actually, okay, this looks like it did pretty well. So here's the parameter space here. What I mean, this is all combinations of A and B that I'm going to consider. So I start here, and then I take a step, then I take a step, then I take a step, then I take a step. And what I'm trying to do, so this is depicting what all the losses are over all these different combinations of A and B. So down here would be like A is equal to 1, B is equal to -5. That would be that point. That seems to have a loss of around 60. Okay. I actually start off at a loss around 100. This is my initial guess of what A and B should be. So I started off guessing that A was like 0.8 and that B was maybe like 1.2 or something. I found that wasn't so great. So what I did was actually looked at the derivative there. Okay, so holding A fixed, I look at the derivative of B, and I found out that B is increasing in this direction. Right, so B is actually going up in this direction. So what I did was I moved the other way. I said, okay, look, if I move this way, so the derivative is telling me that as B goes up, that the loss is going up. So let me actually move B down. All right. Now, if I hold B fixed and take the derivative with respect to A, so that's called the partial derivative with respect to A, I actually find that as A goes to the right, same thing, actually, the loss goes up. So I'm going to move to the left. So notice that my first step, I move both down and to the left. And I find a similar thing for the next step. I move down and to the left. Now at this point, it is still true that as I move up B, my derivative is positive. But actually, if I move right in A, my derivative is negative. So I actually like that. I want to go down. I want my loss function to go down. So in this case, I'm going to go down, but to the right. And so every time you take a step, you're trying to make the loss function go down. So you're going against what the derivative says. So the derivative says my loss function is increasing in this particular direction. I'm going to go in the opposite direction. So derivative tells me the loss function is increasing in this direction here. I'm actually going to walk the other way. And so if you keep walking, with a step that's proportional to the magnitude of the derivative, then with this logistic loss function for a logistic perceptron, you will eventually converge to a global minimum. You will converge to the best parameter choices that you possibly can. All right, so I explained that qualitatively, and I can summarize it very simply. TLDR, we're walking down a hill. All right, we're trying to walk down a hill. So we have some valley here, and we want to reach the bottom of that valley because the bottom of that valley is the smallest loss. And if we look at what's the A and the B at the bottom of the valley, then we have the parameters we're looking for. And so you look at what the model is actually doing. So I plot the choice of logistic perceptron here, and I see that it started off pretty wrong, but then it gets better and better and better, and eventually it gets up to about 93% accuracy. So I start off. Let's watch this one more time. I start off pretty bad. Actually, 94% here. So I start off pretty bad, but it eventually kind of settles in place there. So that's beautiful. This is much better than grid search because I'm actually showing you the grid here just for illustration. But notice most of these points on the grid we never visit. We kind of cut in a straight line. We do a beeline right to the point that we're looking for. And so this actually works just fine in higher dimensions too. It doesn't suffer from the curse of dimensionality the same way as grid search would, because we follow kind of a beeline to where we're looking for. All right? Now, not everything is quite this simple, but you can get a lot of intuition by understanding this example here. Okay? So this procedure has a name, and it's called gradient descent. And so what we're doing is taking gradual steps against the gradient, which is the just the multi-dimensional derivative. So when we, usually when we talk about, you learn derivative in Calc 1, you talk about a single variable. Here we've actually got multiple variables that we can vary here. So that's called the gradient. So we take steps against the gradient until we reach a minimum. And we converge to a good set of parameter choices. So that's how it works. Oops, I meant to say converge. Okay. So that's the lingo there. Now, what if I choose a different learning rate? Okay, so different step size. So we move at a rate alpha times the gradient. What if I instead make alpha just a little bit bigger? So I'll take step sizes that are twice as big. Let's see what that looks like on this example. Oops, I already gave away the punchline a little bit. But what we see is some zigzagging. We actually take a step too far, and then we end up kind of going back and forth along this valley until we eventually do converge, and we settle on a good solution here. But we get some zigzagging up front, so that's something we got to be a little bit careful about. Usually we're not going to have this kind of visualization, but what we'll look at is this loss function over time. And if we see this kind of oscillation, that means that we probably chose a learning rate that's too big to begin with. There are other schemes you can follow, actually, by the way. You don't have to use the same learning rate the whole time. You can actually kind of decrease the learning rate as you go. But anyway, here we're going to keep it fixed. And so we chose one that was too big. All right. What if we actually make the learning rate 1/10 of what it was before? So I look at this now. And it still works, but it takes a lot longer to converge. So compare it to this, where it got down to a loss of 20 by the 60th iteration. By the 100th iteration, we're not even down to a loss of 40. So if the learning rate is too small, yeah, you're not going to see oscillation, so it's very safe. But computationally, it takes a long time, so that might not be desirable. So there's probably a sweet spot somewhere of a good learning rate. So in this particular example, it seems like the learning rate of 0.01 is good. Just to show you another example, here's one that's not linearly separable. This is the disk inside of the other disk. So we're not going to be able to separate this perfectly. So we've got all our positive examples actually in the middle of the negative examples, so there's no way I could actually find one separation point here. but there is still actually a global minimum that I get to. So I think I said this, but yeah, the nice thing about using logistic loss on a logistic perceptron, there's actually one minimum, and you will always converge to that minimum. So there is an absolutely best choice that you can make here. And it turns out to be 60% accuracy. So if I say that everything is a 0, that's what this turns out to be. So it turns out there's more 0 examples than 1 example, so that was actually the best I could do, was saying that everything was a 0, and this finds that. Let's just look at what happens if I make this learning rate too big. Okay, so same example, but I actually end up bouncing back and forth around this basin here, around this valley. And so 60 is the best, but it keeps oscillating between 60% accuracy and 40% accuracy. And so I thought this was kind of interesting, these sort of oscillations that you get. Okay. So while this picture is the most important thing for you to understand, I'd be remiss if I didn't say a few words about the math behind this. How do we actually take the derivatives to figure out the directions to go? So let's say, okay, given an example, x, y, let's think about just that single example. How would we take the derivative of the loss function over that example when we're at a particular point in the parameter space? All right. So if we start off here with our loss function, we can take the derivative with respect to a, treating b as a constant. That's called the partial derivative with respect to a. And actually, if you work it out, it is quite nice in this case. So if you go back and look at the definition of logistic function, you get this really nice equation that says, okay, the derivative is the estimate minus what it's supposed to be times whatever a happens to be right now. And then the derivative with respect to b, so holding a fixed, it's called the partial derivative with respect to b, that ends up just being the difference between the estimate and what it's supposed to be. So that's great. So we have the derivative with respect to a, we've got the derivative with respect to b. Now, one of the things that you learn in multivariable calculus is if you want to maximize the increase in the function, then you walk along the direction of the gradient, it's called. So the gradient is the direction that you get from however much it's supposed to go in this, or whatever the derivative is in this component and the derivative in this component. So that gives me like an arrow. This is how much I would go along A, and this is how much I would go along B. And so if you go along that direction, you will maximize your rate of increase in the function. But that's not what we want to do here. We want to decrease the function, right? So we're actually going to walk against the gradient. That's what I was saying in the picture above here. And so what we're going to do is we're going to say, all right, I'm going to actually change A, for example, to be what A was before, minus alpha, the learning rate, times the partial derivative with respect to A. So whatever that was. All right, so again, I want to move actually against the gradient. Whoops, I forgot to copy the whole thing there. I want to move against the gradient by a particular amount. And so that's the learning rate there, right? And so if I plugged it in, what I find is that actually A, so yeah, let me have this all here to look at. The update rule is just incredibly simple. It says A should be what A was before, plus what Y is supposed to be minus the estimate. Times A times alpha. Okay, so let me say, okay, alpha times A times Y minus sigma of AX plus B. All right, so what we see is, okay, here's your A. I want you to update your A by the learning rate times a times this proportion, whoops, I missed parentheses there, times this proportion of what it's supposed to be minus the estimate of what it is. So if it's below the estimate, then it's telling me I need to increase a. If it's above the estimate, so if this is above y, then it's telling me I need to decrease a. It's as simple as that. So it's really nice with logistic perceptron and logistic laws. And then we see a similar thing for this b here. And that's it. Okay, so here's, you can see this is the where the learning rate factors into the equation. All right, so it just tells me how much am I going to jump from one a to the next. And it literally is just by a proportion of the difference between the two. So you can see if the estimate is equal to y, then I'm not going to change anything, right? So I've settled down. I've reached the best I can be. And so as this difference gets smaller, the derivative gets smaller, and I don't walk by as much of a factor. If this difference is large, it's saying, hey, you're pretty far. Let's take a pretty big step and see if we can get any closer. So that's the way it actually works out mathematically. I'd encourage you actually to go back and plug in some of this stuff in and see just how well this all works out. If you plug in the logistic function here and then take those derivatives. But for now, I'm just going to leave it at this. One modification I'm going to make, though, is that I actually don't just have one example. So I'm going to tweak this a little bit. I actually have all the examples, right? So I have a set of examples. I'll say capital X, capital Y. And so actually the loss function, again, is the sum. So I'll go and grab it up here. It's actually the sum over all of these. And so, but I mean, I've already done kind of the hard part because that just means that I have to sum over all the individual examples here because the derivative is linear. What it means is if I want to take the derivative of the sum of things, it's just the sum of the derivatives. So everything's kind of the same here. But I'm just going to sum up all of the examples. So I'll say from k equals 0 to n minus 1 of sigma. So now I'm going to say this is going to be a times x k plus b minus y k. And so on and so forth. I'll update these details and have them in your notes. But the last thing I wanted to say here was, okay, well, here's a bunch of code that I wrote to make all these animations if you're curious and if you want to generate your own. But I do want to mention that this can be generalized to higher dimensions, and that's what we're going to do next. So you can actually have your input to the function not just be a single number, but a collection, a whole array of numbers. So let's say we had an array with d elements. Then we could say that u is just, okay, so now we have more parameters because we have a coefficient for every element in the array. So it's not just a times x plus b, it's actually a0 times 0th element of x plus a1 times the 1 element x plus a2 times the 2 element x. Now you'll recognize this is a dot product, right? And so we can say in general, u is just a dot product of an array of coefficients, a, with an array of elements, that's my input, plus this bias, b, it's called a bias. And so then I would just feed that into the logistic function and everything is exactly the same. And so we end up getting these update rules here, which are exactly the same as they were. But it's just now I recognize that I'm plugging in this kind of monster thing, this whole big dot product of all the dimensions with a bunch of coefficients there. And so in 2 dimensions, this would have the form, so just as an example, in 2 dimensions, we would have, u is equal to ax plus by plus c. So there we would have 3 parameters. So in 2 dimensions, we have an x coordinate and a y coordinate. So it would be like, an array with 2 elements. And so we have, I called them A and B. I guess up here I called it A0 and A1. But yeah, I would have like one parameter to multiply by the first coordinate, another parameter multiplied by the second coordinate, and then I would add this called the bias here. So I'm putting it in this form. I use slightly different letters here, but yeah, that's the idea. So let me show you. I mean, you can follow this same kind of procedure to walk down the hill. Now, I'm not going to be able to plot the parameter spaces easily because there's actually 3 parameters. I would have to plot a volume, a 3-dimensional grid of A, B, and C. So I'm not going to do that, but I will show you the loss function, and then I'll show you what the logistic perceptron looks like on the data. So here's an example that's linear separable. And you'll see as I walk along, the loss goes down. Looks very nice. And actually, I'll start over again here so you see where it starts off. So we make an initial guess. It's not that good, but it actually ends up moving the logistic perceptron so that it does separate the data perfectly. So that's nice. And it should be able to do that. Because the data is linear separable, I will eventually reach a global minimum where it's guaranteed that everything is on one side or the other. And it's correct. Okay, so here's another example. This example is not linearly separable. This is the one where you have a disk inside of a disk. We end up learning actually that the best thing to do is pretend that everything is positive because there are more positive examples than negative examples. So yeah, we're just going to pretend everything's positive. So we get all the negative examples wrong, but hey, we got up to 60% accuracy because 3/5 of them were actually positive. So that was the best thing to do. So that's what it learns. Just another fun thing, if I make, so here's another example where it's not separable, and if I make the learning rate too big, it kind of jumps back and forth between like 70 and 47%. So again, but you could see that from that telltale oscillation in the loss function. And this will happen, this kind of thing can happen even if it's not such a nice problem. Even if there's not one single min, this is still something to watch out for. Any basin that you find in your parameter space can have this happen. Okay, just to show you, here's the example nicely here. We can get up to about 75% accuracy on this. And if we end up dividing it with this kind of diagonal line there. So anyway, I have code below to do that as well, if you want to play around with that. So now I'm just going to ask you, this is a lot. This is kind of all the mathematics behind gradient descent, which is the technique to learn how to minimize a loss function by tweaking a set of parameters iteratively. And this is actually all that we do for neural nets. I'll explain how this kind of carries through. Well, I have to tell you what neural nets are first in general, but look, we've actually gotten most of the way there conceptually. After this, it's just going to be kind of building off of these concepts. So if you understand what's happening here, what the loss function is, how we're trying to minimize it over time, and how we just take steps in the parameter space to do that, you're golden. So I'm just going to ask you a comprehension question real quick about this, and then we'll continue. Oh, one more thing I should mention real quick. It would be nice to see how easy this is in code if you mash these equations up with what's in the code. So yeah, most of this code is just plotting stuff, but I do want to hone in on the parts that actually do logistic regression. So these are the parts that actually do it, and so it's simple again is looking at, okay, evaluate the logistic function, and then say I want to change A by the learning rate times the sum over all examples of whatever x is times what the output's supposed to be minus what my estimate is, and then the bias, the B, changes by the learning rate times the sum of what the output's supposed to be minus that. So I just want you to see how simple these equations actually are. These two equations here actually are in code. And then for the higher dimensional examples, here's the equations, and it's similarly very straightforward. So I'm updating these 3 parameters that way. All right, so just so you know, logistic regression is dead simple. This actually ends up being an assignment in AI. This is part of what you have to do, but it's in the service of something else. Okay, good. Now we can keep going.